Yep, that's it. Okay, good. Welcome everyone. So let's start. Uh, so we today start with the coursework 4. Okay. Let me remind you some important definitions. So the first definition is for order pairs, right? For all A and for all B, the order pair A and B is defined by the following set. Okay, so this is the definition of order pair A and B. Next, the Cartesian product of A and B, sets A and B. Here, it's so by definition, this is all the Z that belong to the power set of the union of A and B, right? Such that there exists some A and some B, where A belongs to capital A and B belongs to capital B, and Z is equal to the order pair A and AB. Okay, so this is the Cartesian product, but we are not going to write this while we are resolving problems because it's not comfortable for us. So we're going to write the following: that the Cartesian product of A and B is just the set of all these order pairs A and B, such that A belongs to capital A and B belongs to capital B. Okay, so this is enough for us for describing the Cartesian product between A and B. Now, we have to define what is binary relation R. Okay, so R is a binary relation if for all x that belongs to R, then there exists there exists some A and some B, such that x is equal to A and to the order pair AB. Okay, so this is a binary relation. If we have that all the elements of R are order pairs such that well, of this form, okay, and we have that, for example, the empty set is a binary relation, and the Cartesian product A and B is a binary relation as well, right? And what else do we need? Okay, yes, so we can define the domain of R. So the domain of a binary relation R is the following: is the set of all the A's of all, if the set of all the elements that belong to the union of R such that there exists B for such that we have that A and B belongs to R. Okay, so the domain of R is all these points here, all these elements here that belong to this set, such that for each A there exists some B, and we obtain the order pair A and B. In the same way, we can define the range of R. So all the B that belongs to the union of R, such that there exists for each of them there exists some A, and the order pair A and B belongs to R. And that's it. So that's all the definitions we need by now. I guess you already know all this because you studied this on your lecture, and yeah, you should know all this. So we can start with the exercise number 1. So we have the following binary relation R. We have the order pairs 1, 2, 2 and 2. What else? 2 and 3. 3 and 1. And finally 4 and 5. Okay. So this is R. R is the set of the following binary relations here. We need to find some. We need to find some A and B such that R is a binary relation between A and B. So such that R is a subset of the following set, right? And and then we need to find the domain of R and the range of R, and draw the row diagram for the relation R. Okay, so first of all, let me find some A and B. So A and B can be many options here. We're going to find just one of them, and the simplest one that we can think about it is, well, so here solution. So we have, all we have to do is look at the first element in each order pair, right? And this can be A, right? So 1, 2, 3, and 4. That's it, right? So if for any set that contains A, this set A, we can use, so we have to find some A and B. It means that we have many options, right? Many different options. One of them, I mean, the necessary one is this one, right? This is the least possible set that we have. So we can add here, I don't know, 5, right? This works also. This works, right? But why to do it? Just let's write like this, okay? That's enough. And in B, for B, we have the same. So we need to look at just the second element in each order pair. So 2, 3, 1, and 5. So 2, 3, 2, 3, 1, and 5, right? And that's it. If we find the Cartesian product of between A and B, we'll get all the possible order pairs here. And R is going to be a subset of this Cartesian product, okay? And that's it. So this A and B works for us. Good. Now the domain of R, in this case, the domain of R is going to be just A, the set A, right? That's it. And the range of R is going to be just the set B. In this case, for this A and B, do not forget that we can have many other A prime or different sets for A, and this is not going to be true. I mean, this is this, right? So do not forget this. So this is the domain and the range of R. So we need to look at the first element in each order pair and the second element for the range. Why? By definition, right? Because we need to look at the A in this order pair and to look at the B here. And that's it. Now we need to draw this thing. Okay, so let me do it here. So how many elements do I have? I have element 1, 2, 3, 4, and 5, right? 2, 3, 4, and 5. So if I have the order pair A, B, then I'm going to do the following. I'm going to draw here a point for A, here a point for B, and I'm going to unite them by this arrow, okay, in this direction, from A to B. So that's all that I have to do here. So we have for the first element 1, 2. So 1, 2, right? Then 2 goes to 2. So 2 goes to itself, right? Then 2 goes to 3. 3 goes to 1. And 4 goes to 5. That's it. That's all we need. Okay. Great. What else? That's it? Yeah, that's it for this exercise. Okay, I think everything is clear. There's nothing difficult here. And let's continue with exercise 2. So, make a finite sketch for the diagram of the relation on the set of the natural numbers. Well, for this case, I mean, I can do this sketch, but well, something weird here. Okay, I will have to think about this one because maybe there's something special that we have to think about here. I don't see it. So exercise 2 for next class, okay? Just so we go with the exercise number 3. And let me do it over here. By the way, do not forget that the deadline for homework 2 is December 30, right? Yes. So, and the last seminar, I think, will be on December 29. Okay, so the last seminar, we have still 4 more seminars, or 3? Yeah, 4, I think. And that's it. So, and the deadline for homework 3, you have homework 3 as well, will be on January 19. 19, yes, 19, okay. I will write that to the group. So exercise number 3. We have A is a group of men. So A is a group of men, right? And the binary relation APB means that A is a son of B, right? So we need to look at the following things, the following relations. P composed, well, I have to define this, so let me define that here. There's other. Okay, I don't see it. here. Okay, so we have that the composition of binary relations that we are going to denote by this circle here, right? And the definition is that if we have two binary relations P and Q, then the composition of the Q and P is going to be the order pair X, Z that belongs to the Cartesian product of the domain of P and the range of Q such that there exists Y that we have X, P, Y and Y, Q, Z, right? So this is the definition of the composition of two binary relations. So if we have, for example, here, so in this case, we have X and Z. So we have here X, we have here Z, right? And so we want to find the Q composition P. So we have to look at P first, okay? So there should be some Y here, right? So we have X, P, Y. So X, P, Y, and then we have Y, Q, Z. So Y, so we have here Q, Y, Q, Z, okay? And then the composition is going to be X, Z. So we have a composition X, Z. In that case, when there exists some Y for which this condition holds, okay? Good. Now we can continue. So we have this binary set here P, and we need, if we have A, P, B, it means that A is a son of B, right? And we need to define what is the meaning of P composition P, for example, right? And also of the inverse of this relation. So the inverse means that if we have AB, then we will have BA. Okay, I'm not going to write it. You should know this. Okay, so P minus 1, and then P minus 1 composition P. Okay, so let's find it. So P composition P, B. Okay, this is true if and only if, so by definition, there exists some C such that APC, right, APC and CPB. So APC here, some C, and CPB. Okay, so we have that A is the son, right? Means that A is the son. Yes, A is a son of C, and C is a son of B. So this means that A is what? What do you think? Is a grandson, right? Of B. So, and C is the father. So C is the son of B, and C is the father of A, right? So A is a grandson of B. So that is the meaning of this. Okay, so the first one is checked. Now let's look at the second one. We have A, P minus 1, and B. This is true if and only if what? If and only if B, PA, right? So the meaning of this is that A is the father of B, right? So B is a son of A, but since we want to talk about A from A to B, then we say that A is the father of B. Okay. Now next one, we have P minus 1 composition P. Okay, so A, P minus 1 composition P. So again, we have to unite this one and this one. So this is true if and only if there exists some C such that, oh, here I forgot B, such that what? A, P, C, right? A, P, C, and C, P minus 1, B. C, P minus 1, B. Okay. So this is true if and only if, let me write that here, there exists some C such that, again, APC, and here we have to change the order. So BPC, right? BPC. So we have that A is a son of C and B is a son of C as well. So we have that A and B are brothers, right? So A and B are brothers. Wait, A is a son of C, is a son of B. Yes, right, B. Yeah, both are sons of C, so A and B are brothers. And that's it, right? No, and we still have to, we still have to make this one for P composition P minus 1. Okay, so let's do that. So we have that A, so this is number 4. So A, B belongs to P composition P minus 1, B. Again, this is if and only if there exists some C such that A, P minus 1, C, so C, P, A, right? A, P minus 1, C, so C, P, A, and CPB. So we have that C is a son of A and C is a son of B. But we have that this is a group of men. So A and B is the same person, right? Well, I don't know, maybe he has 2 fathers. That could happen, why not? But so A and B are the same person, and they are, and he is the father of C, right? Yes. That's it. Now that's it for exercise 3. Now let's move to exercise 4. So exercise 4. So in this case we have the following binary relations. So less than, less or equal than, and greater than, and greater or equal, right? And we're going to talk about the set of the natural numbers, or over the set of natural numbers, and then we need to look at the following compositions. So this composition here. So less or equal than composition less than. Okay. So we have that A less or equal than composition less than B if and only if, well, again by definition, every time we just have to proceed by definition, there exists some C such that what? Such that A is less than C, right? And C is less or equal than B. Yes. So what kind of relation is this actually? So we have A is less than C, A is less than C, and C is less or equal than B. So we have B, for example, here or here, right? So actually this means that A is less than B. Okay? Yeah, that's it. So we can write that this composition here is actually less than. Okay, so this is the same than this. Next, B. This one. So less composition less than. So A less composition less than B if and only if, again the same thing, there exists some C such that A is less than C and C is less than B. So what kind of relation is this actually? So we have that C so for this case we have that C is less than B, so we have C and B here, right? C is less than B and A is less than C. A is less than some C, right? So this means that B minus A has to be at least 2, right? Yes. So B minus A has to be at least 2. Because we have here at least 1 and here at least 1. This is the distance. So B minus A is going to be at least 2. Yeah, that's it. This is for B. Now we continue with C. Okay. Well, the same thing here. So we have the following one. C is minus 1. So again, we have that A less or less minus 1. Okay, I forgot to tell you. So for this case, of course, it's going to be greater than, right? So if we have the inverse relation for less than, it's going to be greater than, right? You had that on your lecture, I think. So it means that B, if and only if, so by definition this is going to be there exists some C such that A, this thing B, no C, A this minus 1 C, and C less than B, and C less than B, right? So this is if and only if there exists some C such that A is greater than C and C is less than B. So we have that C is less than A and C is less than B, right? So what do I obtain here? So all the possible options that I have are the following. So I can write that this thing here is equal to all to the Cartesian product of the, well, let me write that here. So this thing here is equal to the Cartesian product of the natural numbers and the natural numbers, but without some element. So each of them, we need to take out some element from here. What element do you think we need to take out? So we have that for all possible. So look, this thing here, so all the possible order pairs A and B are going to be such that always there exists C that is less than A and less than B. In the natural numbers, what's the least number? 0, right? So 0 cannot be here in this set, okay? So we need to take out 0. That's it. So this Cartesian product, so all these A and B are going to be here in this Cartesian product. Everything we have to do is just to take out 0. Why? Because 0 is this C here, this number here, C, okay? That's it. Now D. For D we have the following. All right. And then again we just do the same. To C less than A plus B. Well, yeah, but 2C, but no, but why? Why plus? So we have that C is less than A and C is less than B, right? Mm-hmm. What if we have 1 and 1 for A and B, then we obtain 2. So C is going to be 1 also, but C, we have that C is 0, you know, because that's the only number such that this always holds, you know. So, yeah. So we have this if and only if, again, there exists some C such that A less than C and C greater than B, right? So we have that there's always one number among them, right? Some A, so between them. So we have A, B, and C. So what do we need to change here? Do we need 0? Yes, of course. Why not? I mean, if we have A0, C is, I don't know, 1 and B is 4 or anything else, right? So A can be 0. And B can be 0? I don't know. B can be 0? No. No, B cannot be 0, right? So this is, yes. So it means that this is going to be, so for A, everything is possible, so just the natural numbers, right? But for B, but what if, well, actually, not only 0, but 1 as well. No, wait, what am I doing? What? C is greater than A and C is greater than B. No, it's not like this. C is here. C is greater than A and C is greater than C. Yes, this is different. So in this case, every A and B works, right? So this is just the natural numbers Cartesian product by the natural numbers. So every possible ordered pair of natural numbers works for this case. Okay. And that's it. This is D. And we're finished with exercise 4. Now we continue with exercise 5. Order. Sorry, what? B minus A greater than 2. B minus A. Well, yeah, but since we changed it, yes. So it was, but what I was mistaken here, so. About what? About this one. This one. You are asking why this? Well, because we always have C between A and B, right? And not equal. So it means that the difference of B minus A is going to be at least 2. I think it's clear. No? Okay. So we continue with exercise 4 or 5. Let me check. Yes, with exercise 5. So we have to prove that the composition of any binary relation with the empty set is equal to the empty set. Okay? And in the same way that the empty set relation of R. So both of them are equal to the empty set. So all we have to do is the following. Let's assume that this is true, right? Let's assume that this is not true. So there is some ordered pair here, right? So A and B belongs to this set, right? If and only if. Oh, the solution is ready. So we assume that A and B belongs to this set, right? And by definition, we know that A and B belongs to this set if and only if there exists some C such that A empty set C, so that A and C belongs to the empty set, right? And C are B, right? So this thing here means, so you know that, say that AC belongs to the empty set, right? And this is false. Since we have here and, so it's going to be false, and then this is false. So for all possible A and B doesn't belong to our composition of the empty set. So it means that our composition of the empty set is empty. That's it. And for this is the same. All you have to do is just change this here, but it's the same. Okay. Yeah. That's it. So next exercise 5. This was 5, so we continue with 6. Sit here. So we need to prove that, okay, we have to prove some important things here. So we have that P is a binary relation between A and B. And Q and R are some binary relations, okay? We have to prove that P, the complement of P to -1 is equal to P minus 1 to the complement of P minus 1. Okay. Yes. So in this case, the complement of P is just this set, right? So we have the Cartesian product A and B, and we take out P. So this is the complement of P, in this case. Then all we have to do is just use the definition. Then A and B belongs to this set here. If and only if what? If and only if BA belongs to this, to the complement of P, right? But this is possible if and only if AB doesn't belong. Well, yes, if BA doesn't belong to P, right? Because it belongs to the complement of P. And this is if and only if. So if it doesn't belong to P, then AB doesn't belong to P minus 1, right? And then AB, yes, this is if and only if AB, since it doesn't belong to this, then it belongs to the complement. If A and B belongs to the complement of this, to the complement of P minus 1, and that's it. Okay. So this belongs to this if and only if it belongs to this. It means that the sets, that this set and this set are equal. by definition. Okay. Now next. We have, this is a bit more, so number 2, that P union Q composition R is equal to P composition R union Q composition R. So we have to distribution here, right? We have to distribute using the composition, and we unite them with the union here. So we need to prove this. Okay, so let me do the following. Again, we assume that A and B belongs to this set if and only if A and B is going to belong to this set. So B belongs to P union Q composition R if and only if, by definition, what? There exists some C such that A, R, C, right? And C, P union Q, B. If and only if, again, there exists some C such that, so this is the same, just A, R, C, and now we have that, so we have that CB belongs to the union of P and Q. It means that CB belongs either to P or to Q, right? So we have that, and C, P, B, or C, Q, B. And then and now we can do the following. Apply distribution here, right? We know that this is true. We proved it before. So if and only if there exists some C such that ARC and CPB, right? ARC and CPB, or ARC and CQB, right? So we have that there exists some C such that this or this, and this is true. So we can, in this case, so we have that there exists something with this characteristic or with this one. So it means that that there exists this one at C such that this holds, or C such that this holds. Okay, you will see what I meant a bit later. Okay, so if and only if there exists C such that A, R, C, and C, P, B, or there exists C such that A, R, C, and C, Q, B, right? And this is if and only if, so we need to go back. So this means that that, what does it mean? That A and B belongs to P composition R, right? Or A and B belongs to Q composition R. And this means that A and B, that AB belongs to what? To the union, right? So AB belongs either to this or to this, so it belongs to the union. P composition R, union Q composition R. And we are done. Yeah, that's it. So we prove that if AB belongs to this set, then if and only if it belongs to this set. So these two sets are equal. And we actually need to write that for all A and B, right? So for any AB in this set, it should be in this set. So by definition, these two sets are equal. Okay, this was B. Now we want to do C. Let's do it over here. So number 3 or C, we have that we need to prove that these two sets are not equal, but so that P union Q intersection Q composition R is a subset of P composition R intersection of Q composition R. So look at the difference here. We have here the union and the distribution for the union here, right? And we see that it holds and that they're equal. Here we are not proven that they are equal, but we are proven that for the intersection, this is a subset of this one. And we will see why this is not equal, but this is an intersection. This is just a subset, okay? Not equal. So again, AB belongs to P intersection Q composition R if and only if there exists some C such that A R C and C P intersection Q B, right? If and only if there exists C such that A R C and CPB and CQB, right? So look at the difference. Here we have an intersection, so we need to put and, right? And here, since we had the union here, then we needed to put or. Okay. And we can't make some distribution here as well. So we have that such that ARC and CPB and ARC and CQB. Now, if we have if we have, for example, something with two characteristics, so there exists something that is, I don't know, there exists some duck, or I don't know, let me think example. Yeah, a big and black duck. Okay, so a duck that is it's big and black. It doesn't mean that there exists a black duck and a big duck, different, right? So that there exists two ducks with these characteristics, because they can be the same, only one, right? So that is why, in this case, so look, we write here if and only if, right? But no, here, if and only if. Here we cannot write if and only if. We have to write the implication. Okay, so this implies that there exists some C such that ARC and CPB, and there exists some C such that ARC and CQB. And this is true if and only if AB belongs to P composition R and AB belongs to Q composition R. So if and only if AB belongs to the intersection of these two sets, right? So P composition R intersection of Q composition R. And this is what we needed to prove. So what's the difference here is that we don't have here if and only if, we have an implication. And since we have an implication here, then it means that this set is a subset of this set, because all the elements that are in this set belong to this set as well, but all the elements here doesn't belong to this set, right? That's why this is a subset of this set, but they are not equal. Okay, so the reason is this. Do not forget. Well, actually, this that their existence. If we have and, you cannot just like do this and say if and only if. Okay, that's it for C. Now we can continue with number 7. So we have P, Q, and R. These are binary relations, and we have to prove the following. We have to prove that so A, to prove that the intersection of P and Q, the inverse of the intersection is equal to P minus 1 intersection Q minus 1 here. Yes. So let's do it. So we have that P intersection Q minus 1. We can write that this is equal to the following. To P intersection Q minus 1, the complement of the complement. Right? And now we know that this is equal to something that we proved before. So we prove it in exercise 6a. So this is equal to P intersection Q complement minus 1 and the complement of everything. So this is true because of this exercise we proved before, 6a. Now, we have the complement of an intersection. This is the union of the complements, right? We proved this as well. So it's going to be equal to P complement union Q complement minus 1 and complement of everything. So again, the complement of an intersection here is the union of the intersection, or is the union of the complements. Okay? We proved this. Well, you prove it, I think. So, what do we have? And we know that if we have the union of two binary relations here, so the inverse is going to be just the inverse of this one, union the inverse of this one. You proved this one also in class. So this is going to be equal to P intersection minus 1 union of Q intersection minus 1 and everything and the complements of everything, right? Yes. And then this is equal to what? Now we can proceed with again. So we have the same thing that we had for this. So we have that the union, so the complement of the union is the intersection of the complements. Okay, so this is the intersection of this. Q and finally, again because of 6a, this is equal to P minus 1 complement of the complement, right? Yes, intersection of Q minus 1 twice the complement. And then this is equal just to P minus 1 intersection of Q minus 1. That's it, we prove it. Right, so the complement of the complement is the set itself, so it doesn't change. Yeah, that's it for this one. So we have to continue with B. So B, we need to prove that if P is a subset of Q, then P composition R is a subset of Q composition R. Yeah, and if you think about it, this is clear. But so if you think about this thing, you see that this is true, but still we have to prove it, right? So what do we know? We know this, and we need to get this one. So look, it means that P intersection so let me write that. So P composition R is equal to what? So I have to write P here, composition R. But I know that P is a subset of Q. So this is equal to P intersection Q. Right? So since P is a subset of Q, then P intersection Q is going to be equal to P. Okay? And we already proved, we just proved that this is some distribution here. So this is equal, so this is subset actually. So look, this is what we proved here. So this is for 6C. So from exercise 6C, we know that this is a subset of P composition R intersection of Q composition R. And of course, we have the intersection of two sets. Then the intersection of two sets are subsets of the sets, right? So this is the subset of Q composition R. So we obtain that P composition R is a subset of Q composition R. And that's it. So, well, next. We go with C. Yes, with C, okay. So C, we need to prove that R composition of P intersection Q is a subset of R composition P intersection of R composition Q. So we have again some kind of distribution, some kind of distributive property here, right? R composition Q intersection of R composition P intersection of R composition Q. But we see again that they are not equal, but this is a subset of this. And we can see from, we can already see that this is true. This is that way because we have here an intersection, right? Since we have an intersection, then these sets are not going to be equal. Okay, so let's prove it. Okay, so R composition of P intersection Q is equal to everything to the minus 1. So R composition P intersection Q minus 1 twice, right? And this is equal. So we have, we already proved this, it's the minus 1. Wait. Yes, in 7a. Okay, I don't have it already. But we proved that this is equal to, so the same, but we have to change the order. So we have to put R here and P intersection Q here and everything to the minus 1, right? So this is P intersection Q minus 1 composition of R minus 1. Wait, I forgot about the minus 1. No, wait, what happened here? Decomposition. Wait, what am I? So we have 2 minus 1, but this minus 1 apply to all this. Apply to all this. And this minus 1 as well, apply to all this. Then we have this and minus 1 here again, right? So this minus 1 applied to this. So we obtain P intersection Q minus 1 composition of R minus 1. And then we have everything to the minus 1. Yes. We have them. Okay. And then we have this, and we prove that this is equal to P minus 1 intersection of Q minus 1, right? So everything is equal here to. So let me write just the P minus 1 intersection of Q minus 1 composition of R minus 1 and everything to the minus 1. Yes. And now we can make this, so we can apply something that we proved here. So this, right? Again, we applied this thing. So we know that this is a subset of P minus 1 composition R minus 1 later and intersection with Q minus 1 composition R minus 1 and everything to the minus 1. And now again we apply this property, then the minus 1 we put it here and here. So this is equal to so this is equal, we have to, P minus 1 composition R minus 1 and everything is going to be to minus 1 intersection with q minus 1 composition with r minus 1 and everything to the minus 1. And now again, this is equal to, we have to change the order here and put the minus 1, right? So this is going to be equal to r minus 1 to the minus 1 composition with p minus 1 to the minus 1 intersection with q minus 1 to the minus 1, r here, r minus 1 to the minus 1 here composition with q minus 1 to the minus 1. Okay, so we obtain that this is r composition p, right? R composition p intersection with r composition q. Yeah, and that's what we needed to prove. So this set is a subset. Look, here we have the step when we look at that this is a subset of this set. And what else do we have? The next one. Okay, I think that's enough for today. So we finish with this was 7C, AC, I forgot. Okay, that's it. Thank you very much.